Hello, welcome to today's webinar, Demantra Engine Tuning, Why You Should Get Your Engine Tuned. My name is Deb Bryant. I'm the Marketing Coordinator at AVATA, and I will be facilitating the webinar today. Presenting will be Jim Hetherington, VP of Sales at AVATA, and Andrew Calder, Director of Consulting from AVATA Australia. Just a few housekeeping notes. All attendees will be muted throughout the presentation, which is being recorded and will be made available to you. You can submit questions by clicking on the icon in the lower right-hand corner, and responses will be emailed to you directly. And now I will turn the presentation over to Jim for a quick introduction on AVATA. Jim?
Thanks, Deb, and thank you to everyone for joining us on today's call. As we begin, I have one slide about AVATA for those of you who don't know us, and we'll get right into today's content. In brief, AVATA has been an Oracle partner for close to 20 years. And while we have remained focused on manufacturing and distribution industries, we have evolved to be a complete provider of services for Oracle Cloud Solutions, supply chain management, and JD Edwards technology sets. And this breadth, it's important today, as most of our clients in the Oracle community are living in hybrid environments. You know, they're leveraging existing on-premise applications, as well as taking advantage of feature sets provided in the latest versions of these tools offered as true SaaS cloud offerings. And I think this is important and relevant to today's webinar because there are often overlaps, and demand management is an excellent example of this. So while Oracle has completely rewritten what we know of Demantra in a true cloud solution, demand management cloud, it still leverages what is one of Demantra's strongest competitive points, its Bayesian engine for creating a baseline statistical forecast. So today's webinar on tuning Demantra is equally relevant for companies planning to upgrade to current version or those just implementing demand management cloud. So with that, I'm going to turn it over to Andrew. Andrew is one of the, just as a quick background, he's one of the strongest experts in the particular set of activities that's known as engine tuning. And I've seen him work. What our clients appreciate most about him and his approach, I think, is an added benefit is that he does a great deal of knowledge transfer and training during a training exercise or a tuning exercise. And I think this is important because anything we can do to help users understand what the application is doing and why it's creating the output that it's creating strengthens adoption over time. So again, with that, thank you for your time. And Andrew, you could take it from here.
Thanks, Jim, for the great intro to AVATA. I'm Andrew Calder, and I'm going to present the information to you today and welcome everybody to this webinar. So let me just run through the agenda first up, the kind of things we're going to be talking about. First up, I will run through with you some basics of how the Demantra engine works, what makes it tick, the kinds of different functionalities and features that Demantra brings to the table that makes it really unique, and the things that we're looking at when we do engine tuning. And then I'll show you some examples of some problematic forecasts where you can see particular pathologies in the forecast, and we'll talk about the kind of things that would need to be considered to make them better. We'll run through just quickly what tuning means, and also why we would do tuning and some of the benefits that it brings outside of the obvious, just getting the forecast looking better, but some of those other less obvious things as well. Then we'll run through quickly some of the metrics that we employ when we're doing the tuning exercise to try to understand whether we're actually improving the forecast or not, looking at that empirically. And then finally, I'll run through some more details about how our tuning methodology is conducted. and then maybe some final comments at the end. So let's get into it. Okay, so firstly, how is Demantra different from other forecasting packages? Well, there are different types, as you can imagine, and this chart gives a whole range of different types. One key difference from some particular types is that Demantra would be called an objective forecasting methodology, because we take historical data, whether it's point of sale or bookings or shipments, and we combine it with causal factors and have the forecast empirically using that data, as opposed to, for example, creating a subjective forecast using market information or something like that, where you might just type it into a spreadsheet. And indeed, even in Demantra, you can type overrides, but the key thing is to try to get the forecast, the statistical forecast, looking really great to minimize the number of overrides that we do. Within the objective types of forecasting systems, we have statistical and non-statistical. A non-statistical one, for example, could be one where you take historical last year's history and just add 5% or something like that to drive a forecast. Well, that's not a statistical forecast. But Demantra uses a different methodology, statistical, driving it with causal factors, which is really important to the way Demantra works. And then finally, if we're comparing a couple of other methods which would fall under the causal banner, the most common one, which everyone's pretty much heard of, is a best fit forecasting methodology, where a number of different engine models are applied to the data, but then for any particular combination, a single methodology is chosen as the best one and applied to that particular combination. Well, Demantra doesn't take that approach. It doesn't take a best fit approach. It takes what's called a Bayesian approach. Now, what does Bayesian mean, I hear you ask? Well, like best fit, Demantra attempts to statistically forecast using multiple different engine models. That's the same. But unlike best fit, Demantra does not choose only one model as being superior to all others, since in fact the best model may be only marginally superior to other models, or that best model may be what's called overfitted. And overfitted just means that you've actually got too many causal factors compared to historical data points to be really sure about the veracity of the forecast, or the power of the forecast as a predictor of good forecast accuracy. So we want to minimize the number of causal factors that are being used for any particular forecast to avoid this pathology of overfitting. So Demantra performs a Bayesian blend of all models that pass certain validation criteria, and it gives each model its weight according to, firstly, how well it explains the data. That is the backcast fit, which is what you'd expect it to do, and you want the backcast fit to be really good. But also, it gives each model its weight according to the simplicity of the model, and that is to avoid the overfitting. And simplicity in this case, for example, means the fewer number of causal factors that help explain the data. And avoiding overfitting is important when you have many causal factors, because actually great backcast fit is not necessarily a predictor of good forecast accuracy going forward in the future. It might be a beautiful explanation of what's happening historically, but actually have very little power to produce a good forecast in the future. And I'll give you an example. If you had only 12 months of history and you have 12 causal factors, one for each month, January, February, March, and so on, and you produce a forecast with 12 causal factors and 12 periods of history, that means you only have one period of history per causal factor. And so therefore, of course, the forecast is going to look just like a complete replica of the previous year, but you only have one data point. So there's no averaging that can be done over multiple years and multiple data points. And so therefore, the forecast is going to be very uncertain going forward. For example, the system might find very strong seasonality, which is what you'd expect, but in fact, in reality, seasonality doesn't exist at all. So it's actually a false positive, if you like. So the basic idea of Demantra's Bayesian engine, blending multiple different engine models together, is that a mix of engine models will perform better than any one engine model. So this is why we don't take a best fit approach. Okay, So expanding out a little bit further into the components of the engine, well, Demantra has a sophisticated, flexible engine for generating stat forecasts, as you'd be well aware. The thing is, this flexibility means that the out of the box, that is the default settings, are never optimal. Why? Because you have hundreds of engine parameters, many of which are very important to the shape of how the forecast comes out. We've got causal factors, which we've just been talking about, and you can define pretty much as many as you like, depending on whether you have DM, demand management, or AFDM. You have a promotional engine, which allows you to split between base and uplifts. You have a forecast tree, which drive the aggregation levels that you want the forecast to be generated at. You have all the different engine models, regression, crosstons, Holt, intermittent models, and so forth. And then we have the Bayesian blending we were just talking about before. Add to that in the mix the ability to define multiple different engine profiles, and then you have thousands, if not millions, if not an infinite number of permutations to optimize the output. So that's the challenge that we face with engine tuning. So let's just talk about some of the different types of these inputs into the Demantra engine, these functional features, and so we are all on the same page about what we have at our disposal. So the first one, causal factors. Certain of the engine models, all the ones that have the word regression in them, can estimate the impact of changes in the marketing mix and external factors on demand. So this is a really basic example of how causal factors would be used and what we're looking for in the data. So let's say we have this stream of history for 13 weeks, and we see that in this history, it usually averages out to about 100 units per week, but occasionally there are spikes or there are dips in demand. So what we're trying to do is we're trying to understand whether those spikes and dips, and indeed trend and things like that, can be explained by causal factors, or are they just random changes in the data that are driven by consumer or business demand that we have no control of or have no ability to predict. But often there are ways of predicting when those demand spikes and dips are going to come, or at least have some kind of explanatory variables in the past as well. So here, this could be, if we were able to identify this as a price promotion, then we know that around about 100 units of the demand was due to that price promotion. And here, if we have a dip in demand that goes from, normally 90 or so down to 60 or so, and we could maybe identify that as being a competitor promotion historically. And then maybe these 3 weeks, we could identify that we ran a very strong advertising campaign or a trade show or something like that in those weeks. So armed with that information, we can start using that to drive the forecast going forward. If we know we're going to be advertising at some time in the future, then the system can start to understand the relationship between these causal factors and what's going to happen in the future. So rather than just having a forecast that's just heading off in the future in a very flat kind of manner, we can start to model for the spikes and dips as well. So that's the basic idea of causal factors. Now, not every single causal factor, just because you can identify it in the past, doesn't mean you can identify where it's going to come in the future. So one example here, like a competitor promotion, we may be able to say, yes, I know this is why my demand dipped in the past, but actually there may not be any good reason to try to model for that, because in the future we don't know when the competitors are going to run their promotions. So maybe there's actually no point even marking that as a causal factor. But I just wanted to explain that's how, that could well be an explanatory variable in the past, but maybe not really a useful thing to try to model in the future. Okay, so let's run through the different types of causal factors first up. They're kind of going from simplest to most complex. The simplest ones are global causals. These vary by time only, and they're the ones that most people are probably used to. So the trend causal, the seasonality, that's the D1 to D12 causals, global holidays like Christmas, and maybe something that doesn't come out of the box but is often used, something like end of quarter, to explain why we always get spikes in March and June and September and December, for example. So those ones are easy to find. They exist in a table called inputs in the back end, and they're simple because users don't need to worry about them. They're set up once and then they just work. Local causals, on the other hand, vary by time, product, and location. And because they vary by product and location, it's usually up to the users to be marking them to say when those causals ought to be applied. So, for example, marking when out of stocks happened in the past to try to quarantine bad data, or to set average price data. So, but often that can also be loaded in from the back end, or to type in, if we're doing some kind of measure of advertising weight, then maybe you just type in what the advertising expenditure was in a certain period or something like that. But the thing is, these require more management because they are also varying by product and location. And then we have promotion causals, which we use in predictive trade planning and in AFDM, where they vary by time, product, location, and then also promotion. So we actually kind of identify an entity called a promotion, and we put all our promotion details against this entity called a promotion. And then these forecasts create uplifts that are differentiated from a baseline. So one more level of complexity over and above the local causals. And then finally, we have a particular type of causal called activity shaped causals, which we typically use for defining a new product introduction or a life cycle of a product. These causals are so rarely used in Demantra, but actually they're very powerful, and I'm going to show a screenshot of some activity-shaped causals being used in just one moment as well. Okay, so we talked about engine models before, the different types of engine models. So there are around 15 of them in AFDM and 9 if you're using DM. And basically you have many different flavors of regression models. These are the ones that use causal factors. So you have, for example, linear regression, that's this one here, multiplicative regressions, logarithmic, autoregressive, so different types of regressions. And you have some other types of models that don't use causal factors at all. So, for example, Holt and Croston's don't use causals, and some that are designed for intermittent history data, multiplicative multicolor regression for intermittent and regression for intermittent, those two. And finally, you have some naive models which are not actually defined in this list here because they just get used by Demantra automatically as a last resort if all these other engine models fail validation. So you can see you have many different types, and they don't all need to be turned on. Sometimes out of the box they might all be turned on, but they don't all need to be used. Then we have the forecast tree. So this just basically drives the level of aggregation that we want the forecast to be generated at. So typically speaking, the data that comes in to Demantra from order management or wherever it comes from is stored at a very granular level with multiple dimensions. But usually we don't want to forecast our data starting at the most granular level. Usually we would prefer to aggregate it a little bit, for example, maybe to item by organization or item by account, something like that. So we would try to drive the forecast at what I'm calling our desired level. And then if the forecast, if every single engine model fails validation at that desired level, then it will jump up to the next level of the forecast tree and try to forecast there. And if that then fails, then it will go up to a next level. And I've just got a 3-level system here, but in fact, you can have as many as you like. But finally, we'll get to the very top level of the forecast tree that's been defined. And even if that then fails validation, that's when it will then try to use a naive method like a moving average or something to drive the forecast. And typically speaking, you would want about 2/3 or more of your combinations to be driven at this desired level. That's kind of a rule of thumb. And the thing is, when we build the forecast tree, it requires some careful consideration of how we jump up to these higher levels. So for example, if this was an item by account level here, then this next level, do we go up from item to brand and make this brand by account? Or do we go up from account to country, assuming that accounts exist within a certain country, and jump up to this level as item by country? Or do we go even to brand by country or something like that? So it always requires some careful consideration as to what this tree ought to look like, and it's not always obvious. I talked about the parameters before. There are hundreds of them, and they really radically modify the engine's behavior. So for example, valid date ranges. When should the engine not create a forecast? This is the two classic engine parameters, dying time and mature age. That's what I'm thinking of here. So dying time, for example, is used in the sense of, let's say if we haven't had any sales in the last 6 months, at that point we say that the particular combination is dead and it shouldn't produce a forecast. So that's a really important setting. Forecast tree levels, maybe we want to have a particular engine profile or just make a change so that when we look at the forecast tree before, we might have had the top level of the forecast tree set to level 4, but in fact for a particular engine run we might decide we only want to set it to level 3, so we never want it to jump up to the highest level. So you can change those levels. The min 4 level and the max 4 level can be changed for any particular engine run. Intermittency. At what level of intermittency do the special intermittent models kick in? So out of the box, I think it usually is set to something like 40. That means only 40% of the history needs to be nulls or zeros for the engine to consider that particular combination to be intermittent. But when we might decide actually that is too low a setting and we might want to increase it to, say, 66%, so that 2/3 of the data has to be zeros or nulls before we actually call it intermittent. Or we could make it even higher than that, or lower. So these are the things we need to think about. Forecast validation is really important. What constitutes an acceptable forecast? So we talked again about the forecast tree before and how it will jump up to a higher level if everything fails validation. This is the settings which drive the validation. And when we do decide that something is an invalid forecast, so to speak, and we need to jump up to the next level. So yeah, really important settings, those ones. Outlier detection. How aggressively, if at all, should outliers be detected and removed? I mean, the more you detect outliers and remove them from the history, the more likely you are to lower the bias of your forecast, meaning that the forecast is more likely to be under the actuals because you're taking the history. Usually when you apply outlier detection to it, you are stripping out the peaks from the history, which means that those peaks therefore are unlikely to therefore exist in the forecast going forward. So therefore the forecast is more likely to be negatively biased. But often it's required to remove spikes from the history. So we just need to think about how aggressively that ought to be done. In terms of trend adjustment, do we look for recent short trends in the data as opposed to the overall long-term trend that might exist, say, in the last 2 or 3 years of the data? What if the last 6 months is starting to trend down, even though over the last 2 or 3 years it's trending upwards? There are certain parameters that we can set up to allow us to not monitor, but actually drive that behavior so that the forecast will adjust to the most recent trend. There are ways of affecting Bayesian blending just for the relative weighting based on a fit to the latter sales data as opposed to the earlier sales data. So if we wanted to adjust that Bayesian blending behavior, we can do that too. In terms of allocation of how smooth or lumpy is the seasonal forecast allocation from a higher level down to a lower level, there are settings that drive that allocation behavior. And then finally, there are individual parameters for each engine model. So for example, for Holt, there's a parameter called optimized halt, and it can either be set to yes or no. And you might think, well, maybe I'd always want my halt to be optimized, but in fact, there are certain circumstances where it's really dangerous to set halt to be optimized. You actually want it not to be optimized. Otherwise, it will make halt far too responsive to ups and downs in the historical data. And sometimes we want to be more conservative than that. So there are parameters that drive that and many other parameters for other engine models as well. Okay, so I mentioned activity shape modeling before, so we should have a quick talk about that because it's actually very powerful functionality that's kind of hidden away in Demantra. So it's typically used in the scenario of forecasting a new product's life cycle based on a former product's life cycle. So this is a real example from a consumer electronics company in China, actually. So they had this historical data that's in pink here, and that was a particular product, an older product, which was then, as you can see, that so it had an introduction that lasted a few weeks or months, and it gradually disappeared out of the market. And then they came in with a new product to replace it. Now, strangely enough, this new product actually wasn't quite doing as well as the old one. It actually had lower sales. That would usually be unusual. But in this case, that's what happened. And the thing is, the activity shape causals allow one to create a forecast for this new product. As it's introduced, it will start to predict what the tail of this product will look like. See, at the moment, as the new product's coming through, you would expect normally that Demantra would drive a forecast that's heading upwards in this kind of trajectory, because you can see the history is still heading upwards. But in fact, knowing what the life cycle of the earlier product was, we can start to predict that in fact it will not only head upwards, but it will start heading downwards very soon. So that's the power of activity shape causals. Not only does it monitor the shape of what's likely to happen or forecast the shape of what's likely to happen, but it also monitors how high the amplitude of the new product is, and then adjusts the whole forecast appropriately, taking into account the amplitude of the new product compared to the old one. So really useful functionality in Demantra there. Okay, so let's now take a look at some real examples of problematic forecasts that I've come across in the past. Okay, so these are all real examples, by the way. So this is an example from a high-value consumer electronics retailer, and one of the only times I've ever had to deal with daily sales in my whole life. Very interesting data. The thing that stands out in this example is that whereas the history, as you can see, is quite erratic in the sense that it's very up and down, the forecast that was coming out of the system, that's the green line here, was very flat. And as you can imagine, the client was curious as to why the forecast was so flat given all the lumps and bumps in the history. So let's have a look at some of these. At the moment, the problem is there's the only most basic monthly seasonality being modeled right now. And what about all the modeling of everything else? So for example, where is the modeling of this spike here, the red circles? These are both Black Friday spikes. This is a US retailer. Where are they in the forecast? Well, they're missing completely. Where's the modeling of Christmas and New Year? This is the green spike going on here. So that's also missing from the forecast. And where's the modeling of summer holidays back to school? That's this ramp up here and then quick drop off, this other ramp up here and quick drop off. That's completely missing from the forecast as well. Well, I mean, there's very, very minor effect being picked up there. So obviously with such a problematic forecast, the client is wondering what's Demantra doing and why is it coming out so poorly. And this is the one that I've quoted before where I've talked about maybe we wasted $1 million. I'll come back to that at some stage probably. Anyway, it was not easy. It was not a hard problem to solve. All those things can be solved with causal factors. Okay, second example. This is a high-value consumer goods / fashion retailer in the UK, And again, when we look at the forecast, which is in green, compared to the consumption history, which is in blue, you can see a number of things which are kind of missing from the forecast. So the first thing is, why is this forecast looking like it's trending upwards? Whereas in the history, it really looks like, even though we did have a little bit of updrift early on, the most recent history for this particular product is heading downwards. So why is the forecast heading upwards? So surely we have a trend issue going on here in our forecast. That would be very curious to the client to see the forecast heading up like that. And why is the dip over Christmas and New Year so weakly modelled? This is the red circle here. There's a big dip there. That's particularly strong. This one's a little bit weaker, but in our forecast we have this very shallow kind of dip going on. So we're not really modelling properly for Christmas and New Year here at all. And the other question is, what happened to sales over this June-July period here in 2016? Is this expected to be repeated in the future? We did have a little bit of a dip also in 2017 in the same period of time, but I think this last point here actually is really not it's not a real point. It's actually a partial week, so you can probably ignore that one. So we had maybe a little bit of a dip, but we definitely had a very strong one back there. Should that be repeated in the future going forward? If it shouldn't, for example, if that was an out of stock situation, then we should really quarantine that data rather than allowing it to be picked up as seasonality going forward in the future. So again, many things to try to address in this particular example. Okay, here's a third one. This is another high volume consumer goods, and it's a national monthly shipment data into retailers. And as you can see, it's very high volumes coming through. The key thing about this data is that we have this massive spike around June and July in each of the previous years, 2015 and 2016. But in 2017, you can see that the forecast was much lower than the kind of spikes that we were getting in the past. So why is it that our strong historical seasonality is not getting reflected in the forecast? This is a very kind of common question that we get with clients. And I mean, the converse is often also true, and that is you get very lumpy forecasts going forward where the system is finding strong seasonality, but actually it's just random variations in the data. So in the historical data, that is. And this goes back to the previous example I talked about before with overfitting, where you might only have 1 or 2 periods of history for any particular month, which is driving some behavior in the forecast, making the forecast look very seasonal, but in fact, it's only due to random variations in the past, and we shouldn't really be modeling for seasonality. So that's the converse of this particular example, where we need to be modeling for seasonality a lot more aggressively, but we're not. Okay, so that was some real examples. So what is tuning then? Well, basically, tuning is just configuring all aspects of the engine to suit your historical demand profiles, taking into consideration your knowledge of your own markets and your own forecasting preferences, with the aim of improving forecast accuracy with the minimal amount of user intervention. And by that I mean users having to go in and override the forecast. We want the system to generate the best possible forecast. So let's just go back through these again in a bit more detail. So when we talk about historical demand profiles, it's all the kind of things I've been talking about before in terms of causality. Looking for seasonality, trend in the long and short term, but also intermittency as well. Whether the demand is very stable or whether it's very erratic. And this goes to the point of modeling for seasonality, for example. If the demand is very unstable and it's just random, then maybe we should not be modeling so aggressively for seasonality. We should be placing more emphasis on models like HALT, which don't use seasonality. Looking at our life cycle lengths, if they're short, maybe we should be using activity-shaped modeling. Which holidays impact demand, and what other causality might we have in the system as well, promotions, end of quarter, and anything else that we can come up with. So taking into consideration your knowledge of your own markets, that is, for example, cannibalism between new and old products and between different locations. In other words, let's say, for example, that you have a product that's sold through a particular ship from location, and after some period of history, it changes to a different ship from location. So in the old ship from location, it basically, that combination with the item becomes dead after a certain period of time of no sales. The new one becomes live. The thing is, that demand of the two ship from locations for that item probably ought to be added together. So we have this concept of cannibalism, that one has cannibalized the other. The thing is, there's a setting in Demantra that allows you to decide whether dead combinations ought to be aggregated together with live combinations. And it's called cannibalism, or the Agri 99, and there's another setting called Agri 98. These are columns that are stored in MDP matrix. And they're really essential to how Demantra's behavior works, but I find that very few clients have any real understanding of how they're supposed to work, or the fact that they even exist. But they're very important. So again, taking into consideration your knowledge of your own markets, will the historical trend continue? So we might see a trend, a long-term trend through the history, but you might know from your own market knowledge that in fact those trends won't continue into the future for whatever reason. So we need to take that knowledge into account. Differences between products and markets, special consideration for exceptions to general rules as well. So these are things that you know about and that will help inform us when we're doing an engine tuning exercise, how we should approach it. And of course, you even have your own forecasting preferences, that is your own biases. So how conservative are you? Should trend and levels react slowly or quickly to changes in demand? In other words, if you have a big spike in demand in the recent periods of history, should that increase in demand be reflected in the forecast in an aggressive kind of manner, or should it only be reflected in a very conservative kind of manner? These are things that are it's your own preference that drives that. And at what base level should forecasts be generated? When we look at the forecast tree before, do we start at item by ship from? Do we start at item by account? Those kind of things. They're things that we would discuss with you because they're driven by your own preferences. And what about outlier detection? How aggressive do you want to be? So tuning is all about those processes. Okay, but why tune the engine? Okay, let me run through a scenario with you. Let's say your company has purchased Demantra at significant expense in terms of your license cost. You've gone through a whole implementation process where you've spent months configuring the series, the worksheets, integration profiles, everything else. You've loaded data from all the various systems. Everything looks great. Everything's set up beautifully, great worksheets, great processes, except the statistical forecast looks like rubbish. So, for example, the forecast does not make any sense in light of the historical sales patterns. Users get agitated. They're being forced to make overrides left, right, and center. They're feeling it's a waste of time. They're feeling it's unproductive. And now they're even complaining about wanting to go back to Excel. And then you, as maybe the demand planning super user or project team, become skeptical that Demantra can even produce a decent forecast. And you've got all these post-purchase doubts. And this is that example I was saying before about maybe we wasted $1 million. That's how they felt. And this is why you need to tune the statistical engine, because that kind of scenario really is untenable. You should be getting the best possible stat forecast out of Demantra. Now, that's not to say that every single client can get a beautiful stat forecast, but because if you have very random demand, then by its very nature, you will have a forecast that's going to have a high degree of forecast error. But what we should at least be trying to do is minimize those forecast errors and minimize the really obvious things that aren't right, where, for example, you have a downtrend in historical data, but Demantra is forecasting an uptrend, something like that. We want to avoid those kind of situations. We at least want to minimize the bias, even if the forecast error is high. And there are other benefits that come from tuning as well. So, for example, tuning allows you to streamline the whole forecasting process, because you could have many thousands of combinations, too many to review each cycle. So you just want the engine to at least produce for you the best possible forecast, so that you know that you don't have to go and review every single combination. And a good stat forecast enables you to reduce the manual forecast overrides and possibly your bias as well, because usually people, if they're going to override a forecast, they override it on an upside to try to make sure they get more stock out of the warehouses or something like that, reserving stock, that type of thing. So we want to avoid that possibility of that being required. And you know, the good thing about Demantra is the system keeps learning from the most recent history. So as the history comes in, the Demantra learns from that history, and it starts to adjust its trends and levels and responses to causal factors. So which users can be expected to continuously monitor the changes in demand patterns all the time? Well, they can't, especially if you've got thousands and thousands of combinations. So you want the system to be doing that for you. And conversely, you want to allow the users to focus on exceptions. In other words, the subset of high value items and or those with the worst forecast accuracy. And indeed, as part of a tuning engagement, we can build for you matrix levels that allow you to do that kind of focusing on those problematic combinations very easily. So that's something we should talk about at a different time. Other benefit, it helps you establish realistic limits of mate production. In other words, what fluctuations are random and what are predictable based on causal factors. This is exactly the point I was making before about some forecasts will always be problematic because of the randomness of the historical data. But we want to at least try to work out, well, what part of our data is random and what part of it is predictable via causal factors, and setting up causals properly will help to do just that. And finally, another big benefit, if you're calculating safety stock using a root mean squared error methodology, where basically you're relying on the forecast error metrics coming out of Demantra, and if you can lower that forecast error, then you can lower your safety stock. It's such a no-brainer. It doesn't cost anyone anything to do that, and can save, you know, millions off your bottom line just by improving it by a few percentage points. Okay, so let's take an example of a kind of a tuning example, right? So let's say we've got this historical data here. You can see it's quite erratic over history, but there are some patterns there. It's erratic in the sense that it's up and down, but there are some patterns. And when we compare it to this history, which is point of sale history, when we compare it to some causal factors that we have loaded into the system, in this case, we've got everyday shelf price in green, and we've got the average retail price, in other words, the promoted price in red. You can see that there are times when it's been on promotion historically, and then this blue line just identifies when it has been on promotion. Actually, you can see there's a little bit of problem with some of the data here coming in, but that's a different issue altogether, where in fact we have our everyday shelf price lower than our so-called promoted price, but we could ignore that for the moment. The point is, we've got a number of different promotions that have been identified throughout the history, lining up with this history data, and we can also see that there are spikes that are correlating with Christmas here and here, and also with Thanksgiving here and here and here, and there's another Christmas spike. And also that you can see there's an overall downward trend in the data as well. So we would want to be modeling all those different things. And this is the same data after careful configuration, otherwise known as tuning. Okay, so what do we see here? Well, firstly, we see that the historical data, when overlaid with the forecast and the backcast, so the backcast is just the forecast actually represented as a mathematical model over the top of the history, we can see that number one, there is a baseline in the light blue, and there's the forecast including the uplifts as well in the dark blue. So we can see, for example, here that this is a promotion where the history in black has been modelled with the models in dark blue and light blue. So you can see all these have been modelled as promotions through here. Wherever there's a difference between the dark blue and the light blue, these have been modelled as promotions. And you can also see that the Christmas effect has been strongly modelled as well, as indeed has the Thanksgiving effect. And we also see a downward trend coming through the data also and being projected through into the future. The other thing we can see from this graph is that these are the engine models that have been chosen by Demantra and blended together. BCMR is the BWINT model, Monte Carlo, modified ridge regression and regression, and it's been generated at this level, level 2, which is the level that we're actually looking at here at the, on this graph, which is an item or a promoted group by account level. And to kind of prove that this forecast model has been useful is that we did a calculation of the holdout mean absolute percent error, and it was only 5% or roundabout. So what I mean by that is that the data 4 weeks up to week commencing 19th of December 2016, so 4 weeks in around about this period here, was held out from the history. So the history that drove this forecast was somewhere back in October here, and this actually is part of the forecast, it's not part of the backcast. So you can see that, that in fact we had a very close, tight match between the history and the forecast that was generated. So while a low MAPE like this is not absolute proof, or the backcast fit here is not absolute proof that we have done a good job of the modelling, it's indicative that we have done a good job. Okay, so let's talk a bit. We just talked about metrics a little bit just there. Let's talk about them some more. So I'm not going to go into this in any kind of great detail, but just suffice it to say that the metrics that we're choosing here are trying to help us in the tuning process to decide that when we make a change to some forecast parameter, or we add a causal factor, or we add or remove engine models, all those type of things, we're trying to work out, are we improving this forecast or are we not? And like I just said before, the way we normally do it is we would set our last date backwards so that we've held out some of our history as if it did not exist yet. And then we run the forecast, and then we compare that forecast to that held out history, and then try to work out, well, how close are we? Have we done a good job of doing a prediction here? And we use a number of different metrics to work that out. So the first one is just the total forecast error. So at some level of granularity, so for example, we'll pull out of Demantra all the combinations of item by account, and we would then add up all the errors of all the item account combinations, the errors between the actuals and the forecast that we generated, and then we just add up the total absolute error, divide it by the actuals, and that will give us a total forecast percent error. So that's one way we do it. Another way I do it is I look at a weighted MAPE, where rather than just using the total forecast error, what I'll do is I'll do a very similar process, but I'll cap the errors at 100% for each combination. So for example, if the forecast was 100 and the actuals were 20, that means we have a difference of 80 over 20, so it's like a 400% error. I'll cap it at 100% because what I'm trying to do is not penalize over forecasting more than under forecasting, because if I have an actuals of 20 but I had a forecast of 0, then the maximum error would be 20, which is 100%, whereas an over forecast will be penalized too much potentially. So just to try to equalize between over forecasting and under forecasting, we have this weighted MAPE methodology which strips out those over forecasts a little bit. And then finally, we have a bias calculation where usually at the whole business level, we'll just add up all the forecasts, add up all the history, and then compare that forecast versus history. And what we're aiming for is that it should be a 0% difference overall. So we know that some forecasts will be over, some will be under, but overall we're expecting, all things being equal, that our overall forecast should be pretty similar to the history. And that's what we're aiming for. So this is an example of a spreadsheet that I use to do this. So what I do is I extract out all the data, for example, at the item by account level. In this case, actually, it's item by country for a particular month or a group of weeks or a number of months or whatever we decide. In this case, it's just 1 month. I extract this out and I put it into a special Excel spreadsheet where I've got a number of metrics set up. So let me just take you through quickly what this looks like, but without going through too much detail. So we pull out the forecast that we generated, the actuals that existed in that particular month. Then I have some columns here for forecast value and actuals value. These ones are identical to each other because, in fact, for this particular client, they weren't storing any pricing information. So I wasn't able to blow that out to a value, to a real value. So that's why it's got the same values as the history in units. Then we do a forecast minus actuals, and so in this case, so for example, we got 504 minus 263 is around about 240, and then we have an absolute error. So this one minus 99 is changed to 99 because we're making it absolutes. And then this is the driver for my weighted MAPE calculation, where I've capped the errors at 100%. So for example, here we have a forecast of 77 and actuals of 20, but I've capped the error at 100%, even though in fact it's around about 300% or something like that. Then we use this calculation to drive a weighted MAPE, and what we're looking for is at the overall level across all the items. I mean, there's thousands of them in this spreadsheet. Overall, I'm looking at a weighted MAPE, and it's at 19.7%. That compares, by the way, to the total forecast error of 23.8%, which is the one that doesn't have the uncapped errors in it. And also another weighted MAPE I've done where rather than weighting it on actuals, I've weighted it on actuals plus forecast. And this means that any item that has a forecast that has no actuals, that had a 0 in that month, still gets a weighting. Because if I'm weighting on actuals only, and there's a 0 actuals in that month, then it won't get any weighting at all, and that can be problematic. So there's two different types of weighted MAPEs I've done here, and these numbers may have some meaning, but actually the most meaning they have is when you compare one engine run to another. So we're trying to see whether these numbers decrease overall from one engine run to another when we've made changes to parameters and so forth. So we're looking for reductions. And in terms of bias, you can see there's an overall bias here of minus 3.8%, and that's because forecast is 317, actual is 330, and the difference between those is 3.8% at the top level. So we're trying to get that one down to 0, like I mentioned before. Okay, so there how I use the metrics. Okay, what about AVATA's tuning methodology? Okay, so there's a couple of initial steps that we start with. The first thing is that we start with a high-level review of your current Demantra configuration, how your forecast process works, what's the input data, how the forecast is then being used. For example, is it being output to ASCP, and at what levels is it being output? So it might be output, for example, at item by organization. And if that's the level it's being output at, then we might consider thinking that, well, maybe our forecast also should be driven at that same level, and maybe our metrics also should be monitored at that level as well. So it just helps to inform how those metrics and forecast tree ought to be configured. And then this is a really important point. For existing Demantra systems, we ask you, the client, to identify examples of problematic forecasts and also give us some commentary regarding what you perceive the issue to be in each case. because we don't want to make assumptions about the way your forecasts are coming out. We might perceive, for example, that that your forecast is fine or terrible, but in fact you might disagree because of certain assumptions you've made or certain biases or understanding in your marketplace. So we're really very keen to get feedback about those things before we start the process. We talk about assessing the current Demantra forecast accuracy metrics if you have some, and agreeing on new metrics as well. We get you to set up a tuning instance of the engine for us, so the latest copy of production typically. And then we want to establish a baseline forecast against which to measure the results that we're getting as we make the tuning changes. We might decide on a subset of items or family or locations to benchmark, or just take the whole database, and then possibly run a naive forecast as a baseline to compare to if there's no existing forecast in your system. If we're starting a brand new engagement, a new implementation of Demantra as opposed to an existing one. Then in terms of analysis, we create worksheets for analysing and benchmarking. That is the comparison of forecast versus history with tables and graphs, just like I've shown you in the previous slides. And we want to check whether your basic settings are correct. So for example, if you have an existing forecast tree, is it set up correctly? You have to have multiplications of many to one going up the forecast tree. And I have seen examples in the past where some clients have not had that set correctly. And in fact, the forecasts that are coming out of Demantra are completely wrong, just simply because the forecast tree is actually set up incorrectly. We want to make sure that all your global causals are being populated right now, and there aren't some that are missing. Whether all the causal factor setups are correct. There are some checkboxes that need to be ticked in the causal factors, and sometimes they're not checked correctly. And just take a look at what key parameters you're using right now. Is the dying time appropriate? Is the mature age appropriate? There might be other ones as well that need to be changed, which are causing radical problems with the forecast. And also reviewing key matrix settings such as prediction status, do for, and the ones that I mentioned earlier like Agri 98 and Agri 99, that's the cannibalism settings. Okay, so then we go through and we do an evaluation of your demand history, just like I was showing earlier. We want to work out what are the drivers, that is the causal factors of demand over time. We've talked about that a lot. Are the drivers more predictable than the demand itself? So there's no point trying to model for a causal factor really that is less predictable than demand itself. So for example, someone might say, we should be modeling for the economic cycle or something like that. Well, the economic cycle may be much more difficult to predict than your own sales history. So it's probably no point trying to model for it. And anyway, the correlation between the economic cycle and your history may be so weak as to be immaterial. And when's it right to stop digging for more causal factors? There's a certain kind of cost benefit of just trying to bring in more and more causal factors. And in fact, we want to avoid overfitting, as I talked about before. And we don't want to model for causals that don't really exist in the data. I gave the example of modeling for seasonality where it doesn't really exist. And in my experience, you should really model for causal factors that you can see with your own eye history, not try to model for things which are so minor that you can't see them. You're just probably going to introduce mathematical uncertainty into the forecast. And how many years of history should we use? And at what time granularity should we be using weeks or more than that? We need a certain decent amount of history to drive seasonality, for example, but we don't necessarily want to go back too many years because that older history data, just as it gets older and older, just becomes less and less relevant to the most recent modelling. How much of the demand is random fluctuations? How many customers are responsible for the demand? Sometimes that's interesting and useful. Intermittency, is the data accurate? Are there any gaps? I've found some clients where we've looked at the historical data and we found big gaps in there, and they were not even really aware of that those gaps even existed, and they needed to be rectified before we continued with the tuning process. And of course, promotion data is notoriously bad in just about every single client we've ever talked to, and often needs to be cleaned up, and there's often a big process required to do that. And we also like to check, that is, graph the overall shape of the demand across the whole business or by some business group, just to see what the overall patterns are across the whole business. That's influential when it comes to looking at the bias of the forecast at the top level. So we've evaluated demand history, then we want to evaluate the forecasts that are coming out of the system as we generate our initial forecasts, or we look at the forecasts that are already coming out from the existing system. So is the existing forecast a reasonable projection of the demand history? All these things I've talked about before. Is the trend being picked up? Is the recent level decent? Is the seasonality being picked up? Should we be even predicting seasonality? Are the promotions well modeled? What about other causals? Should we be looking for other causals? Which engine models were used and at what levels of the tree? So that's those two series that I showed you before, just quickly, the one that said BCMR and level 2, that's an engine model series and a levels series, and it's very useful for helping to understand what the engine behavior is at this after any particular engine run. What does a backcast fit look like? It doesn't always matter, but it usually does. So the better the fit, usually the better the forecast, but not always. What is the weighted MAPE of the forecast? Is the forecast accuracy any better than a naive forecast? Obviously, we want to be improving on a naive forecast, just like a moving average. Otherwise, Demantra is not adding any value. Are outliers currently getting picked up, and how many of them? And should we be picking up so many, or less, or more? And which causal factors are getting used? All these are important to understand the behavior and how to fix it. And then what we do is, of course, we iteratively modify these configurations using all the different types of aspects of engine behavior, the engine parameters, the forecast tree, etc., etc. All these are at our disposal to modify. And we report and discuss these results with you guys, the client, talk about what we found, talk about whether we need to change some certain behaviors, what are your biases and preferences, and then we repeat these steps as we go through more and more combinations and try to find more and more issues in the data. And then obviously, once we've come to the end of our tuning cycle where we're happy with how things have come out, then in terms of deliverables, well, there's deliverables through the tuning process, and that is, for example, PowerPoints with screenshots of the examples and the discussion points and the key settings and the reasons for keeping or changing them. And we run go-to-meeting sessions where we go through those PowerPoints with you and discuss what we found. But finally, at the end of the whole engagement, then we will deliver a tuning configuration document that contains all the relevant engine settings and how we've changed them. And also we would have one or more tuned environments as well, typically dev and or prod, depending on whether that's in scope to modify prod or to hand over the tuning document to you guys and then let you go and make the changes in prod yourself. But I wanted to make one more final statement, and that is that we also think that training is really important. We love to train clients in the engine and forecasting concepts so that users don't feel that Demantra is a complete black box. We want you to be productive and engage in the system and really take ownership of the system. And I think the way to do that is to be able to spot problems yourselves and have an idea of what Demantra is doing and how you got to the forecast that it is producing for you, and what therefore might be a way of solving it without having to bring in consultants to do it for you. And that doesn't mean that we can't help you. Of course we can, and we'd love to do that. But it's always good to have some degree of self-sufficiency to feel more engaged with the system and be able to solve some basic problems without having to continually resort to manual overrides or get frustrated with the system. So that's our approach as well, is to try to make sure that you're well trained. So some takeaway thoughts. Well, firstly, the idea of tuning often is kind of one of those scary ideas that makes people apprehensive, but really what it is just good configuration of the engine. Bearing in mind there are so many different ways of doing that it can be a bit intimidating, but in the end we want to just do the best job of configuring the engine. And why should you get your engine tuned? Well, it's really a small investment in time and money to get the most out of Demantra. And we just talked about minimizing user frustration as well. We definitely want to do that also. And then finally, we want to train key users to appreciate how Demantra is producing forecasts in order to solve problems rather than just putting in overrides, and we think that's really important. So, well, that really wraps up what I wanted to share with you today. Thanks for taking the time to listen in. Don't hesitate to reach out to us if you have any questions about the content that I've presented to you today. And over to you, Deb.
Thanks, Andrew and Jim, for that wealth of information. And thank you all for joining us today. We invite you to contact us if you would like to know more or are interested in talking with us about getting your Demantra engine tuned. You can learn more about our services on our website, as well as our social media platforms. Thanks again for joining us, and have a pleasant day.